All right, lesson 11.1, our last chapter. Goodness of fit. Our key idea here is we are using distributions to see if the observations are quote unquote normal. And what we mean by normal actually is does it fit the pattern? So instead of looking to fit a line like we did in chapter 10, we're looking to fit a pattern. In this particular case, the distribution that we'll be comparing to is chi-squared. All right, so a goodness of fit test is a test of a hypothesis to see if it fits the distribution. Nothing really new in the, well, I guess there are two new ones. Variable world, we use O and E, the observed frequency and the expected frequency. How often does something show up? And how often is it expected to show up? That's what those mean there. K is the number of categories or the cells that you have in your particular pattern that you're looking at. Requirements, it should be randomly selected data, and the sample data covers the frequency categories. That means you can't have a frequency category open, and that'll become apparent in just a moment. Your expected frequency count needs to be greater than or equal to 5. Good morning.
Good morning.
I'm recording. Don't mind me. I'll be with you in just a moment. Your hypothesis test is H sub 0 and H sub 1. The frequency agrees with the distribution. The frequency doesn't agree with the distribution. There's your test stat variable. You won't be actually having to calculate this manually. I'll be showing you how, on StatCrunch how to get your value and on the chi-squared table. Your degrees of freedom are k minus 1. It's always a right tail test. And again, a couple other things. Your expected frequency, if all the categories are equal, then we just take n divided by k. Whereas if they're not all equal, then you take n times whatever your probability is of getting that. And here's now the decision making when you are done with your test. If the differences between the observed and expected are small, then we have a large p-value and it's a good fit. You fail to reject H sub 0, okay? So that means that you are in this region here, okay? If the differences between there are large, again, between O and E, then we have a small p-value, and this is not a good fit, so we reject H sub 0. All right, and here's our example. 100 weights of California residents are submitted. The last digit is in table 11.2, and we'll look at that over here in just a moment. Analyze last digits to see if these are reported weights or actual weights. Notice the frequencies of 0s and 5s. So anyways, here is the table of data. And again, we strip out all the numbers except for the last digit of their weight. And notice these two categories here, 0 and 5, how large they are compared to the rest. So right away, we're a little suspicious that people rounded their values of their weights, and they probably rounded down because people have self-image problems. All right, number 1. The claim, we suspect that the weights were self-reported. So our null hypothesis is that all these probabilities are the same, and then our alternative is that at least one probability is different, okay? So they don't all have to be the same. So these probabilities would all be 1/10, or sorry, yeah, 1/10, okay? No significance level is provided, so we're going to assume a 5%. I think in your problems in the homework, they'll probably tell you what alpha should be. Chi-square distribution is used to test the goodness of fit. So that's what we compare it with. Enter your data, and you'll get a result something like this. I'll show you that in just a moment using our StatCrunch in Benford Law in the second problem. In this case, notice the p-value is less than alpha. So if we come over here and we look at the p-value, less than alpha, and so we reject our claim that they are all equal. So there is sufficient evidence to support the claim that the last digits do not occur with the same relative frequency. So the data is self-reported and not reliable. All right? You can see here in terms of the manual calculations of this, when we get the 212.8, and that would be that chi-squared value up here, and there's our critical value. So you can see we're well beyond the critical value, and that's why the probability value is so small. But when we do that formula and we subtract the observed minus the expected frequency, then we get these large values, which when squared become incredibly large, and so that's why we are we have such a large chi-squared value, which puts us in a low probability. All right. Benford's law, detecting computer intrusions. In this case, we're going to be looking at sample 2. And this is network traffic data. I wish I could explain it to you more, but right now, this is like milliseconds or something like that. It's the amount of time between when one packet arrives at your computer and the next packet arrives, or finishes arriving, and then the next one comes. And so the claim is the digits fit Benford's law. If they do fit Benford's law, then we've got no problems. We don't have to worry about some sort of intrusion going on. All right? By the way, this is called inter-arrival times. And again, it's just the leading digit that we're taking here. So we take and set up our p-values to Benford's laws, yes? And we look at each one. And the claim is that they all equal Benford's value, and then obviously our alternative is that one of them does not. Again, 5% is our assumed significance level. So we enter these observations, and let me show you up here. Let's see if I can do this. Camera. Okay. And you're going to be going up to stat and goodness of fit, chi-squared. Observed is sample 1. Benford's is in Benford's, and compute. Okay, and there's our chi-squared value and our p-value. Okay, I think this was sample 1, not sample 2. I should have done this on this sample here, so I would have gotten the same results as I had on here. Sorry about that. I actually ended up doing your homework problem because that's the one that you have to do in your homework set of traffic flow, at least in the book ones anyways. All right, back to the notes. So notice I didn't get the same values here, and that's because when I did my problem on the computer screen, I used these values here in sample 1. All right, in this case, we have a p-value of 0.8186, and we can see that that is greater than 0.05, so we fail to reject. All right, there is not enough evidence to reject the claim that the leading digits fit Benford's law. So therefore, this data, it means that we weren't hacked, there was nothing malicious going on. Carry on. We can see that also a plotting of the observed values versus the expected values from Benford's law, and we can see it roughly correlates to that pattern. Tomorrow, we'll look at contingency tables, 11.